Hello, I'm Michael Firth, Product Marketing Manager for Texas Instruments Motor Drive Products. Today I'm here in Kilby Motor Lab, and I want to spend a little time discussing the basic operation of a BLDC motor. I'm going to focus in on a sensored architecture. To begin the discussion, let's first take a look at the electromagnet. So in this slide here, you see the BLDC stator. Now this is the stationary part of the motor. It's got 12 electromagnets. Each one of those electromagnets is just a wound coil, and when you wind the coil in a helical manner, you generate a magnetic field along the axis of that coil. That magnetic field, the strength, is proportional both to the turns and to the amount of current flowing through that coil. Now, one of the really cool things about an electromagnet is you can change the polarity by simply reversing the direction of the current. So in this example, we've got current entering at the top, and it's generating a north pole at the top of the electromagnet. If I were to reverse that current direction, basically have the current exiting at the top, I would generate a north pole at the bottom of that electromagnet. Now let's take a look at how these electromagnets are used to spin a motor. So here we've got the stator again. We've got 6 poles this time. We've got basically 3 pole pairs. And one of the first things to point out is how it's wound. And the way they wound these motors is they use a single winding to create a pole pair. So for example, A and A bar are actually the same winding. Each one of those, A and A bar, will create an opposite polarity, so a north and a south pole. If you add the rotor is a permanent magnet, and it's typically either made up of some type of ferromagnetic material or rare earth material. It just depends upon the requirements of the motor in terms of performance and size and cost. To get that rotor to rotate, you need to commutate the stator field such that the rotor is always chasing that magnetic field. That sounds pretty complicated, but it's actually pretty simple. You just simply turn on and sequence different pole pairs. So to get that rotor to advance from A to C bar, what you need to do is you need to turn the current off in A and A bar and turn the current on in C bar and C, creating a north and south electromagnetic pole, and that rotor then is attracted to it and you get rotation. Now you just simply repeat this 6 times. This is where you hear the 6-step commutation, and that rotor will rotate 360 degrees. Now the trick is, when do you turn on that adjacent pole? So you've got no positional information in the diagram shown here, right? You don't know where that rotor's at, so you don't know when you're supposed to turn on that next magnetic pole. The turning on, the timing is extremely critical. You want to always maximize the torque, and if you turn on that field too early or too late, you're going to have performance issues. So what typically happens is they add sensors to the system. Some of the more common sensors are resolvers, optical encoders, Hall effects. Resolvers are typically in military, heavy industrial applications. They're fairly expensive, extremely high precision. Optical encoders are more popular, but I would say Hall effects for commutation are definitely the most popular, as at a lower cost. And again, what these encoders do is they give you that rotor positional information. So your system knows the position of the rotor, and then it knows when to turn on those electromagnets. Well, I hope this video was helpful, and stay tuned for the next installment where we'll actually talk about sensorless BLDC operation. If you've got any additional questions or looking for information, please see our website at www.ti.com/motor. Or if you're interested actually in spinning some motors with BLDC drivers, take a look at our DRV 8313. It's our latest 3-phase BLDC driver, 2.5 amps, and it's available on the web. Thank you for your time, and good luck spinning those motors.